Thank you, everyone. How do you feel about Aaron's talk? Your brain hurting? Well, if it doesn't hurt, you can take a look at his code here. So my talk will be a lot more gentle, and I'm not trying to blow your mind or anything. I'm just trying to yeah, we're going slow and easy. We also have another hour, and I'll have APL and NumPy code side by side. I'm not trying to pitch you APL. I was just trying to show you how to do NumPy things in APL. So the next time you want to do some array operations in NumPy, you can also consider APL as another tool at your disposal. So yeah, don't switch if you are using NumPy. Do what works for you. And so the bit about covering briefly, I actually changed my mind, and I'll present the code in a more organic fashion. So feel free to just ask questions and interrupt me midway, because if you don't ask questions, I'll ask you questions. And yeah, so I'm leaving out some details, just keeping it more about the code. Before that, a bit about me. I studied applied math in undergrad, and I knew APL from YouTube videos. I've always been interested in programming language things, and APL just showed up on my recommendation. It's videos from the Code Reports channel. The man behind it is Connor Hoekstra. Then I got a job offer programming in APL, and pretty much learned it from scratch on the job. The company is a BCA Research, and I'm not an employee of a Dialog. I'm their customer. Unlike Aaron and David, Josh, who will be before and after me. So what are we doing? Well, I'm just picking a simple Morse law model. So that's a math formula. Some real data from a CSV. Then number 3 is some math. Long story short, I'm finding a line of best fit from the CSV data. So yeah, we'll do some comparisons between these models. Then we will do some plotting and save our results and figure out how to share them, export them. Then if we have time, we'll have a chat, and I have some demos prepared to fill the time. This demo itself is modified from the Morse law tutorial from numpy.org. So what are our dependencies? On the Python side, we have packages, NumPy, and matplotlib for plotting. On the APL side, we have sharplot. That's a graphics library that ships with the Dialog installation. The interface is in an object-oriented style, as you will see. And the Pineapple is an optional dependency that's also open source and external. It lets me run APL code from Python. So trigger warning for APL users. You will see butchered NumPy style APL because I'm doing it for the sake of a comparison. So sorry in advance. So yeah, here's the code. We do the imports, and we import pineapple, and I defined this little run function that runs APL code. Oh, and the APL line starts the APL interpreter in the background. So what's going on here? So on the Python side, we have here, yeah, and you can see everything that starts with a run is APL. So what Python is doing is the formula listed above. That's a Morse law formula with two constants, a and b. So we define the constants in NumPy is np.log, 2 divided by 2. In APL, np.log, 6 characters long, 6 letters long, is a one character long primitive function in APL. And why does it look like that? It's like a star inside the circle. Well, the APL exponential function is a star, and the log is the inverse of exponential. So we just put a circle around the star and call it a log. It also looks like a log. So yeah, that's the first part. The second part is a divide. It's a backslash in Python. In APL, it's just a division symbol, because why wouldn't it be? Yeah, same story here. It's minus is minus, and multiplication is a multiplication, of course, in APL. That's the little x here. Now we are defining Morse law in Python as a lambda function. So the input is a year, and the rest of the calculation you know. The Python definition is a lot shorter, so I kind of added a space to make it line up to the Python. So you can see it's structurally similar. You define your input variable, you do the calculation. Your functions are a lot shorter. But yeah, that's the idea. And the detail is that the Python syntax for anomalous function is called a defun, a direct function. Is that you run calculations you define in these curly braces. And so what's this diamond here? That's not really in a curly brace. You can think of it as a semicolon in Python and C. It's a statement separator. But I don't actually need that. It's there because there's the Python interface is not perfect, so it won't run unless I put the diamond here there. Yeah, it's a work in progress. And yeah, I can evaluate. I can pass the result from APL to Python. So I'm doing a simple comparison here. So you see the AM and BM from Python. That's from these lines, these indented lines. And I'm just running an APL expression, A and BM. And yeah, they are close enough. Oh, my bad. Yeah, thank you. Omega is, so by default, omega is the reference to the input to your Lambda. But yeah, I can reassign it and then make it more readable. Thank you. So did I miss anything else? OK. We're good? OK. So let's check our Lambda functions. So there were this many transistors in 1979. What does Moore's law say about 2 years later? So yeah, here's the calculations in Python. You code the Lambda function, and you do string.format to pass your results into a string form. The APL, yeah, it's the same. It's a similar story. Yeah, the equal is the arrow. I think I don't need to go over that. So the format function, string.format function, is another one letter long primitive function in APL. And the print function is this box assign, and basically assigning to the, I guess, output buffer variable. And yeah, there's no string formatting syntax in APL. I just do it inline. And so in here, I'm formatting this variable to the 0 decimal place. But I'm not done yet, because the way 0 format works is that if I try to format it to a decimal place, it adds a white space at the beginning. I'm not sure why. APL has its reasons. So I'm dropping the first blank character to make it consistent with what we have up here in Python. Yeah, same story here. We can pass in arbitrary computations, and the results are exactly the same. Now let's read the CSV data. So the CSV data contains these headers. So we should probably inspect it before loading it, the file content. And we are saving the columns that we are interested in to better names. Well, first to data, then better names. So let's try printing the first 10 rows. And yeah, we are not using Python now, but the Jupyter interface allows me to code shell commands. So yeah, head, that's what head does. It shows the first 10 lines of a file. Now, in APL, you can also code a shell command with quad sh. Quad is the box. And you can think of quad as the prefix for the APL standard library. So it's like more utility functions that deals more with systems. So they are called system functions. Let's look at. So yeah, the first output looks pretty good. But before the first output, I had some problems. So that's if I just call head directly, I end up with this stuff down here. So you see this A with a hat. That's not what I want, and that has to do with how APL stores symbols on the low-level side. So the workaround is to just fix each of the characters. And the fix is do a quad UCS. It's a universal character conversion. So I first converted to like numbers for each character. Then I reconverted to UTF-8. So then our output is fine. But we don't want all the columns. Yeah, we just want columns 2 and 3. So to do that, there's a NumPy function that takes a CSV, and you can tell within the options you can specify the columns you want, and you want to skip the header row. In APL, you can read. There's some missing functions in APL, but in the quad CSV function in APL, you can only specify the separator. Then you pass in you pass in your file name, and these two options I'll go over in a bit. But yeah, so we take in the CSV as a whole. We are not trying to modify anything. Then we index into columns 2 and 3 of the CSV, and drop the header row. We just do what we want. We don't need to specify it in an option. But yeah, I can do the same in Python, or at least I tried. So that's a parsing. So ideally, this data CSV1 colon thing is the same. It's doing the same things. But when I try to load everything in the CSV, I get an error because not the types in the CSV file is not consistent. There are some strings, and there are strings mixed with numbers up here. So you have like a processor. Where's my mouse? Yeah, you have a processor. That's the content of the file, and you have these these strings that are not numbers, and np.load text has problems with that. So I can't even load the CSV and do what I want in the first place, which goes back to these two options. So don't worry about the funny 0. It's an empty vector. It's just a placeholder. But the 4 here is telling the quad CSV function that if you see a number, try to convert it to a number. And if you see a string, leave it alone. And yeah, that's a pretty basic feature for reading CSV, so I'm not sure why I can't do it in NumPy. So yeah, let's give our data better names. So we are grabbing the column. We're just basically naming the columns. The column 2 is here, and the 1 is a transistor count. Then we print the first 10 values. In APL, it's pretty much the same story. The indexing syntax is very similar because APL did it first in the 60s. And yeah, here's how you can also add comments in APL. These comments are a hack to be a string. Why are they not comments? Because that's another problem I ran into with the Python interface. If I comment one line, the rest of everything I have after it becomes commented. So yeah, I'm going to open an issue later. Then yeah, it's okay. So same story here. :1 is :1 because I like one-based indexing is useful in this case. So then I print out exactly the same thing. I just inputted the tabs directly here, since APL is already using special characters. So well, what's another tab? It doesn't really matter if I use it as a /t. Oh, here's another funny one. This is also another limitation with the Python interface. And OK, well, how are we doing on time? OK, we'll go over it if we have more time. But yeah, same result. Now let's do some simple linear regression. So we define this y variable. It's a log function, one letter long. And we are using these squares to find the line of best fit. And don't worry about the math. Here's because NumPy would do it for you. You call NP polynomial fit degree 1. Then you convert the model to get the constants here. In APL, we just do it directly. But yeah, I don't do linear regression a lot at work or linear fits. So I have to find it somewhere. Maybe someone else defined it. So I visit this EDM search engine, aplcart.info, and I want to know how to do a linear fit. And it told me to do it this way. So I just kind of copy pasting the boilerplate, which is roughly 4-character long boilerplate, 4-letter long boilerplate. And what this OK, I'll go through the computation step by step, briefly, because I'm running out of time. So I'm just basically solving a matrix formula, and I'm OK, and that's enough. So I'm doing a matrix division down the road, and so why does it look like this? So it's a division, and I just put a box around the division, and then now it's a matrix division, because I guess a box looks like a matrix. And I'm extracting the model variables using this assignment syntax, and I print out the same thing, and yeah, this is here again. So yeah, that's a lot shorter visually. And yeah, Python did it afterwards. Python also has this syntax. Now let's look at some more computations. So it's doing a formatted string this time. It's not calling .format. And yeah, it's a similar style in APL, but we don't need a special string syntax. And yeah, same result. All right, that's plot our results. So we have 3 things we want to plot. The least squares, the line of best fit. Moore's law, the lambda we defined earlier, and the CSV data as a scatter plot. Where the Python tutorial uses the 538 style sheet, and it's pretty pretty obvious if I can find my mouse. Yeah, so it's a classic step-by-step style. You plot you take the log of the y-axis and plot with captions and labels. Here's what it looks like. Yeah, pretty good. Now, the sharp-plot library in APL does not have a style sheet. So to get it to look the same, I wrote my own. It's a long story. And this is object-oriented APL in practice. And yeah, it does look OO. And here's the actual plot. Yeah, you see we're defining similar things here. And yep, it's not exactly the same because I got lazy. But you get the point, right? The colors and the legends are good enough. Let's zoom in on our results, in particular, say 2017, and compare these three things again. Well, and to get a better idea of the scatter plot, the Python plot uses an alpha, which makes the overlap more visible. But before that, there's a little computation we have to do to narrow down the numbers. Oh, OK. I'm not spoiling the APL. So in NumPy, I think this is NumPy syntax, which says, OK, so I'm indexing into a Boolean. This one year is 2017. Then we print the max, mean, and the mean of our 2017 data points. Then line space because plot. Then we do more simple calculations. So the APL for APL, you cannot index into a Boolean in APL. However, there's another one-letter long function that converts a Boolean array of like zeros and ones into where indices where the ones are. And this where function is this iota underbar. I don't have funny stories to tell about it. It's just a variation. It's a play on index, which is I, or iota. Next, oh, right. But this way of programming is extra butchered in APL. No APL, we don't use this style in practice. Instead, we can index directly into a Boolean with the filter function. So it filters out where the zeros are in this Boolean. So that's what you should do. Okay, I'm doing it here just to show you. Yes, you can do it this way if you really want to. Next, we do some printouts. And so first we have max, and that's how you spell it. I'm not going to go into the details, but you can think of it like just like a hard-coded value. So yeah, this means max. Don't question it for now. And this, if you squint a little, you can see this little up style. It's like there's a bar up here, and that gives you an idea that you want the max. And this down here means that you want the low, the mean. Mean here is a short definition in APL, but we can do better if I have time at the end. And yeah, same things below, and the same outputs. Okay, so that's plotted in Python. Yeah, nothing much here. Just we define the alpha here, and let's look at the plot. So yeah, you can see, when the color is darker, there's some more overlap between our data points. Now the APL is more verbose than the Python version, but yeah, it's O again. Let's look at it. And browsing for the right things to use is also not as straightforward as Python. So I gave up when trying to make the alpha dots, so you can't really see the overlap in this version. And yeah, this box is alpha as well, but I got lazy. So what can we conclude from this? Just a short conclusion. These squares on the blue here is closer to the mean of our data points, while Moore's law is closer to the max. Okay, let's share our data. So we are exporting in 3 ways. We're on the NumPy side, we're saving as a NumPy array that you can read with NumPy. An APL namespace, which does similar things. It's also possible to save an APL array to a component file, which is more efficient. But the interface is a little dated, I would say. And we save to CSV in both Python and APL. We have the np.saveText function. And in APL, we use the same CSV function, because why introduce new names? Okay, let's make a note for the array we're going to save. So we're constructing a string just by modifying it. Yep, nothing new here. And in APL, okay, there's no /n support for APL strings, so I defined my own new line string with the quad UCS 10. I think 10 is the number that corresponds to new line. This is a common pattern you'll see in APL programs. This is an NL variable. And yeah, we pretty much, but structurally it looks the same. We just add a new line at the end. And okay, and the outputs are the same, right? Yep. Let's use save z in NumPy. So we give it the file name, nodes, year, transistor count is transistor count, predicted is predicted. We're just repeating all over the place. In APL, we can save our variables into a namespace by just referring to the variable names once. And that's this coordinates function creates a namespace. Then we can define a name within the namespace the usual way. So now we are going to export the namespace into text form and save it. And okay, so we pass this underscore namespace to sc.dialog.array.serialize, another long name. It's going to become more formalized soon and shorter, I hope. Where do I know how to do this? I searched the docs. Then this quad input here is a write function. Input stands for native put. Why native? I don't know, but the reason feels old. And yeah, we save it to a file name, and the one means overwrite. There's another way to do this in one line, but it requires some setup. Okay, and let's view our results. We have, so you can load a npz file with np.load. You can load a APL namespace file with native get. This little sideways U here is a pick, so you're picking the first element of ngget because that's the format of the output. Then you call dialog.array.deserialize to deserialize it into your result. And so the printouts are structurally similar as well. The Python result is a dictionary, and you can index into a dictionary and look at the first element here. I mean, the second element, yes, that's a 1 because of zero-based indexing. In APL, you can index into a namespace with dot. That's a pretty common syntax, and the second element is 2. Okay, and I'm formatting to 13 decimal points, and since I'm using I'm formatting to a decimal place. Again, I have to drop the first blank and print it. And yeah, close enough. Let's look at what files we have, the files that we generated. So yeah, let's list our files, another shell command. You can call a shell command again. I'm not using the conversion trick because thankfully I don't have funny file names. Okay, now that's save to CSV. And there's another NumPy function for that, save txt, with a header we're defining. So the difference is that we have to format our results to a 2D array because it's a CSV. Okay, so same story, define header. Define head, yep, same result. Okay, now to build the 2D array, the matrix, we're going to use np.walk and np.newAxis. So here's a short analysis of the shape of our data. So year.shape is shape year in APL. This another one-letter long function gives me the shape of an array compared to another 6-letter invocation. I'm counting the dot here. Next, so you can see the shape is this long. It only has one number because it's a vector. Now, if we add np.newAxis to our shape, we get an extra number in the shape. That's a 1 here. And to add an extra, and this here basically turns the vector sideways into a 1-column array. So that's upside down. Aaron? Yeah, the table. But that does not do it generally. So yeah, there's a shortcut if you wish, but I'm trying to stay general here. And yeah, we look at the shape again. So that's you see how the APL way is just it's half as long in this case. Yeah, there's no new axis and shape. Okay, so that we are calling the bulk function by adding a new axis to all of our vectors, a lot of repetition. In APL, it's a one-liner. It's a wrapping over. So the first thing we did, I forgot to use the other thing here. But yeah, this is the one-letter function that also turns a vector into a one-column matrix. Then I do the comma. Comma here is a concatenate. And so APL is smart enough to recognize that when you concatenate a vector and a one-column matrix, it will just turn it into a matrix as well. So I can just keep on doing that, and that we get our output as a matrix. Okay, and we're saving the text file with a header, and let's take a look at it. Yeah, looks fine. For APL, headers are a tricky business, since the quad CSV function does not have a header option, unless you're adding a header to every column of your CSV. But that's not what we're doing here. We're adding free text. So I'm doing a little hack here with a regex. Yes, you can use a regex from APL, and basically get the same thing. Input is a file write. And yeah, in this case, I have to use the conversion trick again, because there's a funny character that does not show up on the screen. Yeah, so I guess I don't really need it now. Okay, so that's it for our little exercise. What functions have we used? We used load text, which translates into using the CSV function, indexing and dropping the first row. So we are composing functions here. Log is a composition, a symbolic composition of exponent. Lambda here is curly and omega. It's called omega because you put your variables after your definition. You can also put variables before, and that will be referenced as alpha. Okay, now we are onto the plot. Sine log y is a log scale in sharp plot. It's longer than Python. Plotting is longer as well. Okay, so the first 10 is a 10 take, and the indexing is. I think I don't need to go over this since we just did it really recently. So yes, don't do it this way. Okay, don't filter this way. You have a built-in function for that, so do it this way. Block is concatenate and table. New axis is this table function as well. And save z is longer in APL. You have to serialize it first, then you save it. And okay, so there are some points you may have noticed here. NumPy has a lot of these specific function names. especially for reading and writing files. In APL, we prefer to put together more composable definitions to achieve what we want. And yeah, sometimes we are not just composing functions, but composing symbols. And notice how you don't, for these NumPy functions, what's going on underneath? There's another nested function definition under here. It's less so in APL, but you can see it's still there for some things. But yeah, when you have these one letter long functions, it's easier to debug since you don't need to step into anything. The ecosystem as well. The ecosystem is more mature in Python. I don't have to define my own plotting style, and I don't have to manually export things. But in APL, it's not that hard to just find a workaround or hacks in my use of the Python interface. And this is just rolling your own stuff because you know how to already. OK, so yeah, that's it. Do we have time for questions?
A couple of minutes.
OK. Oh, there's one there. Yeah. Oh.
Yes, thank you for the talk. So I have a question about the last slide, which was a nice comparison, like the table, I guess one but last, yeah. So can I have like the best of both worlds? Because obviously I really like the APL notation for manipulating arrays, but when it comes to, plotting stuff, serializing stuff, I don't know, communicating over network or stuff like that, I imagine there are better tools, so it's tools that are better suited for this kind of things. So do you know of any implementation or embedding of APL into anywhere where I could, as easily do the array processing as an APL and do, plotting as easily as in Python?
Well,
like that.
The code here is all ran in Python, right?
Right. Yeah, I was about to add this one caveat that maybe I don't like, the strings, and I put all my code in strings, and I have no syntax highlighting. I don't have a good debugging story, I imagine. So
yeah.
Is it the best that we can have these days? Or
Okay.
is there anything?
Okay. So do you have a question or answer? Okay.
Yeah, so this stuff right now is designed to integrate with the interpreter, but part of the design of the newest versions of codefunds is to make it retargetable to the languages like Python so that you can write a native APL file and then produce a native Python file that directly integrates with the rest of your stuff. And so it will make the interface a lot easier between the two languages and a little bit faster. But also in terms of like communicating over the network and representations and data, APL has one of the best like auto serializations that you have. That's what the component file systems are. They've got like journaled file systems with compression and serialization. And you have mechanisms for serializing data for transfer and compression over the networks in a binary format are already built into the interpreter. So yeah.
And Edward?
My guy answered already. So my question was, what's the model of the integration for the Python to dialog interface? Is it like spinning up a separate dialog process and talking over standard in and standard out?
Yes, for the first part, is starting a dialog interpreter on the background. And I think they talk over TCP.
Oh, they talk over TCP?
Yeah, because there's a special protocol to interact with the APL interpreter.
Okay, interesting, thank you.
It's basically a client-server connection to an APL.
Okay, and anyone else?
Thank you very much.
Okay.